In this video, we're going to talk about section 5.2, the eigenvalue method for homogeneous systems. I want you to recall section 5.1, where we introduced some concepts from linear algebra, and at the very end touched on how we can utilize them to solve systems of DEs. In particular, if we have a system, we can set up our coefficient matrix, which is comprised of the coefficients in front of all of our variables x1, x2, x3, and we can also set up our vectors x and x prime as x1, x2, x3, and x1 prime, x2 prime, x3 prime, so as to order our system of differential equations in a more algorithmic way. This section is going to focus on how to come up with those solutions, in particular linearly independent solutions for those systems. And again, we're going to rely on methods from linear algebra. So I just have a statement here at the beginning that talks about a theorem from the previous section 5.1. And the key here is that if we can find n linearly independent solution vectors x1 through xn, then we're in business. Because once we get those n linearly independent solutions, we can take a linear combination of them, and this expression x of t then becomes our general system. So in this section, we're going to focus on how to find these solution vectors. To do so, let's introduce some concepts from linear algebra. We're going to begin by identifying an eigenvector. We're going to denote eigenvectors by the lowercase Greek letter lambda. And what we want is a number lambda. You'll note that it can be 0 or non-zero. And we want that lambda to be such that if we take a matrix A and we subtract off lambda I, that when we take its determinant, that equals 0. Now recall that when we take a determinant, the determinant of a matrix is not a matrix. It is either a value, a scalar value, if your matrix is comprised of all scalar entries, or it's going to be some kind of an expression if you have a variable in there. This equation up above here, determinant of a minus lambda I equals 0, is called the characteristic equation. Now, this is a term borrowed from linear algebra. However, we have seen the phrase characteristic equation in this class, and it's no coincidence. What we were doing in chapter 3 is we were setting up characteristic equations and solving for the roots, and we were using those to identify individual solutions for the differential equation. We're going to be doing the exact same thing here, only in vector form. Once we have found our eigenvalues, we want to find an associated eigenvector. So an eigenvector is a non-zero vector, and this is super important. Your eigenvalue can be 0, but your eigenvector must be non-zero. It's a non-zero vector such that this equation holds, that when you multiply your coefficient matrix A by V, you get out the scalar lambda V. So lambda, again, is your eigenvalue. V is the eigenvector. If we move lambda V over, we can write that as AV minus lambda V equals 0. And then using properties of vectors, we can factor that vector out. And it's equivalent to saying A minus lambda I times that eigenvector equals 0. So more often than not, we're going to use this rendition, which is very similar to this equation up here. But the goal here is to solve for both the eigenvalue and then the associated eigenvector. So far, we're not even talking about how this relates to differential equations. We're purely discovering some concepts that would be covered in a linear algebra class. So in this next example, again, no differential equations. We're just given a matrix A, which is a 2 by 2, and we want to go through and find the associated eigenvalues and their eigenvectors. So let's begin by computing eigenvalues. So our goal is to compute the determinant of A minus lambda I equals 0. We have A up above. Let's remind ourselves what I is, the identity matrix, and we had introduced that back in 5.1. That's the matrix with 1 on the diagonals and 0 elsewhere. So this is our 2 by 2 identity matrix. So what we want to find is A minus lambda I. So that is going to be the matrix we were given, 4, 6, 1, negative 1, minus lambda times this identity matrix. And I will, in general, never show this step right here. What I'll do instead is I'll jump straight to the characteristic equation. And I'll say, okay, well, all that is the entry in A minus lambda along the diagonals. For the entry in row 1, column 2, it would technically be 1 minus 0 because we have a 0 in that entry. So I will generally not write the minus 0. Same for this next entry in row 2, column 1 would be 6 minus 0, but on the diagonals, we're always subtracting off a lambda. I want to equate this determinant to 0. Now, since this is a 2 by 2, the determinant is easy to compute. We have 4 minus lambda times negative 1 minus lambda, and then take away 6 times 1 equals 0. So let's go ahead and expand this equation completely out, and then we'll want to factor it. So we get a negative 4, then a negative 4 lambda and a positive 1 lambda would be a negative 3 lambda plus lambda squared minus 6 equals 0. So our characteristic equation is lambda squared minus 3 lambda minus 10 equals 0. This is our characteristic equation, so maybe I'll note that here with the CE. Now we want to solve for the lambda values that satisfy this equation. And so at this point, this is about where we would get to in chapter 3, except for instead of lambdas, we would have r's. So now we want to solve. This is going to factor, I believe, yes, so lambda minus 5, lambda plus 2. So what we get are the following eigenvalues. Lambda 1 equals 5 and lambda 2 equals negative 2. So let me box those in. That was the first thing we were supposed to find, were the eigenvalues. And then we want to find the associated eigenvectors. And I'm going to run out of space here. I'm going to have to move into the margin of the next page, but that's okay. So first, let's talk about lambda 1 equals 5. And let's find its associated eigenvector. So let me scroll back up here and just remind you guys of what it means to be an eigenvector. We want to use this equation right here, where we want to now plug in lambda there where it says lambda. So I'll underline that right there. We're going to let lambda equal 5. And our goal is to solve for this v. So we want to find the vector where this equation is true. All right, so we're going to look at A minus 5i times some v equals 0. So what I'm going to do is I'm going to look back up at this equation, but instead of looking for a determinant, I just want the actual vector. So now I'm going to have, or not, excuse me, not vector, I want the actual matrix. So I want A minus 5i. And so you'll notice all I'm doing is replacing all the lambdas with the 5. V is what we're trying to solve for. That vector, we don't know what it is. So I'm going to call V some column vector AB. And our goal is to find A and B. And then I want to equate this to 0. So here's our setup. The question is, what must A and B equal? So what I'm going to do is I'm going to carry out the matrix multiplication, and I'll start by taking row 1 by column 1 and equating it here to 0. So what I get for this row is 4 minus 5 is -1 times A plus 1 times B. Whoops, I didn't write my A. So this is a -A plus B equals 0. And then now I'm going to do the bottom row. And what that gives me is a 6A minus 6B equals 0. So you can see fairly quickly that these two equations are actually equivalent, and both of them give you that A equals B if you shift them around. So we didn't solve for A and B explicitly, but we were able to identify a relationship between A and B, and the relationship is that A and B must be equal. So what this tells us is that there's infinitely many eigenvectors associated to the eigenvalue 5, but they all are going to look the same in that all of them are going to have equal entries at A and B. So you get to make a choice at this point. What do you want to let A and B equal? Remember, there is only one forbidden eigenvector. And let's go back up there. That forbidden eigenvector is the 0 vector. The eigenvector can be any vector that satisfies this equation so long as it's non-zero. So 0 is not a choice. Let me not write it like this. 0 is not a choice for A and B, but any other choice is fine. So I'm going to say choose A equals B equals 1. So then what our eigenvector is, and I'm going to call it V1. It's of the form AA, and I'll make the choice 1, 1. So here is our eigenvector. All right, so this is the eigenvector associated to lambda 1 equals 5. We want to do the exact same process for lambda 2 equals 2, or excuse me, -2. So I am going to just do that right here in the margin. So I want to take my A minus lambda I, which is going to become a +2, 1, 6, and -1 plus 2. And again, I'm going to randomly call my lambda 2 eigenvector AB, and I am always equating this to 0 by the definition of what it means to be an eigenvector. So if I do my dot product multiplication, I get 6A plus B equals 0, and I get 6A plus B equals 0. So I get the exact same expression here. In any case, this gives me B equals -6A. So what I like to do is I like to first write out my eigenvector in generality. And what I mean by that is we started by saying V2 equals AB. But now I just found a relationship between A and B, namely that B can be expressed as -6A. So now I'm going to write this as A comma -6A. And now you get the choice of choosing what A value you want. Again, the only forbidden A value is 0. That's the only one you cannot choose. So I'm going to make a choice. Choose A equal 1, and in that case, my eigenvector becomes 1, -6. But I'll just write maybe in a different color here that you could have chosen, whoa, that is super thick. You could have chosen let's say B or A equals 10, in which case your eigenvector would be 10 and negative 60. So it makes it really interesting to grade these problems because many of you will have the right answer, but many of you will have different eigenvectors, which will make your answers look different. So this is a prime example of a section in the back of the book where, yeah, if your answer looks like the back of the book, great, but just because it doesn't mean it's wrong. It could be that you picked a different eigenvector. So let me box this in. All right, so again, this was an example that was purely borrowed from linear algebra. We're not seeing any differential equations here, but now we want to explain why these eigenvalues and eigenvectors are important in regards to systems of differential equations. So that brings us to our next theorem. We want to let lambda be an eigenvalue of the coefficient matrix A, and then if V is an associated eigenvector, then here's how we're going to come up with a solution. Very, very similar to what we were doing in chapter 3, that root of the characteristic equation, which we're calling lambda, sticks into the exponential function there, e to the lambda t. So we were previously seeing e to the rt, now we see e to the lambda t, and then this eigenvector is the vector out front. So you're just going to take your exponential function and multiply it by your eigenvector, and that is a solution to the differential equation. All right, so let's lay out a method. Here's in general how we're going to solve these systems using this eigenvalue method. We want to, first step, solve the characteristic equation. You're always going to set this equation up. The equation is never going to differ. And then depending on how large your system is, you're going to find all of these eigenvalues. So if it's a system of 2 DEs, you're going to find 2 eigenvalues. If it's a system of 3 DEs, you're going to find 3 eigenvalues, and so on and so forth. Next, you want to attempt to find n linearly independent eigenvectors. So you're going to find, first of all, the eigenvalues, lambda 1 through lambda n, and then you hope that they each admit a linearly independent eigenvector. The linear independence is important. We're going to see how to handle situations where we get linearly dependent eigenvectors in 5.5. But in this section, we're always going to have linear independence. If you are able to get n linearly independent eigenvectors, then we can set up our solutions, which are all going to be of the same form. Oh, shoot, and there's a typo here. So please correct this subscript to a 2 and this subscript to an n. So you're always putting your eigenvalues in the exponential function, and then the associated eigenvectors are out front. Once you can confirm that these are linearly independent, either by using the Wronskian or by using some theorems that we're going to see here a little bit later, then your final solution is going to be the linear combination of those n linearly independent solutions, and that's going to be your general solution. So this is the end goal right here, is to take this linear combination. And then we'll note there are 2 ways to write this. You can write this in the vector notation or the scalar notation. And so I'm going to show you guys both notations so that you can decide which one you prefer. All right, so here's the eigenvalue method laid out. Let's go ahead and work some examples. All right, we have another system of 2 equations and 2 unknowns. So what I like to do first is just write my system out in that matrix notation. So I'm just going to let x prime be the vector x1 prime, x2 prime. And let me write out my coefficient matrix. So for x1, the coefficients are 4 and 1. So those are going across the top row. For x2, the coefficients are 6 and negative 1. So there's my coefficient matrix. And then, of course, we're multiplied by x, which is x1, x2. Now, you'll notice that this coefficient matrix, 4, 1, and then 6, negative 1, if I scroll back up, That is precisely the matrix we had in this previous example. So we already found the corresponding eigenvalues and eigenvectors. So those eigenvalues were 5 and -2. So I'm just going to write, by the previous example, we found lambda 1 to equal 5, lambda 2 to equal -2, and then the associated eigenvectors. Remember, they can be any scalar multiple of what I'm about to write, but we had chosen 1, 1, and I think it was 1, -6, but let me scroll up just to make sure. I want to stick with what I had. Yeah, 1, -6. All right. So normally you're going to have to work through this step as part of your eigenvalue method, but we already worked this out. Now we're going to set up our solutions. So remember that first solution is going to be V1 e to the lambda 1 t. So in this case, it's 1, 1 e to the 5t, and x2 is similarly going to be v2 e to the lambda 2t, which is 1, -6 e to the -2t. So these are our two solutions. Next, we would like to identify if they're linearly independent, because we can't just take a linear combination of these unless we know they're linearly independent. So we can dump these guys into the Wronskian. And remember, the Wronskian is the determinant of the matrix, who is formed by taking these two solutions and entering them as columns of the Wronskian. So I'm going to go ahead and just distribute my exponential in, and I'm going to write it as e to the 5t, e to the 5t, e to the -2t, and -6 e to the -2t. And let me compute this determinant. It's a 2 by 2. So that's going to be a -6 e to the 3t minus e to the 3t. So what I'm getting here is a -7 e to the 3t. And I think we can all agree that that is non-zero. So we conclude linear independence. All right. So now that we know that we have found our eigenvalues and we found our eigenvectors and the corresponding solutions are linearly independent, we can write our final solution. So I'm going to begin by writing it in the vector form. So x of t as a vector is going to be c1 times my first eigenvector, 1, 1 e to the 5t, plus c2, 1, -6 e to the -2t. So I'm literally just slapping a c1 and c2 right in front of those solution vectors up above, which I just starred, and adding them together. So this would be the vector form. Now, sometimes it's beneficial to look at each individual row. So looking at the top row and the bottom row separately. And so if we want to do that, that's called the scalar form. And so for the scalar form, I'm going to write out x1 of t and x2 of t. I am intentionally not putting vector bars on top of those x's because they are no longer vectors, they're scalars, hence the name scalar form. And all I'm going to do is read off the top row. So that's going to be a c1 e to the 5t plus c2 e to the -2t. And that's going to be your expression for x1. And then x2 is going to be across the bottom, c1 e to the 5t minus 6c2 e to the -2t. And so then those two scalar expressions are going to form the scalar solution. So let's box this in. All right, and there is our solution wrote in two different ways. All right, so in this example, we had two real and distinct eigenvalues, namely 5 and -2, and then we just rolled with it. I have a note here which I have covered up partially, but what it says is, in order to apply the method of eigenvalues, our eigenvectors must be linearly independent. So we had already noted that, but this linear independence is absolutely crucial for us to find our general solution. I want to make a note that if our eigenvalues are repeated, we are going to fail to have linearly independent eigenvectors. This is bad. We're going to handle this case in 5.5, which is the next section that we'll discuss after this. However, in this section, we're going to focus on real and distinct roots and also complex conjugate pairs. So those are the ones that we're going to handle. But first, we have a super important note here regarding real and distinct eigenvalues. It is always the case that the eigenvectors associated to distinct eigenvalues are necessarily linearly independent. So in this case, I'm not proving this, I'm stating this as fact. In this case, if ever you're working these eigenvalue problems and you get real and distinct eigenvalues, I just want you to note, just literally write one sentence, real and distinct eigenvalues, so the eigenvectors are linearly independent. And you do not need to then check the Wronskian. As long as you just state that sentence, you can skip the Wronskian and just jump straight to your general solution. All right, so to end this section, we want to talk about complex eigenvector or eigenvalues and how we're going to handle that to find our eigenvectors and then our corresponding solutions. So what we're going to do is we're going to just start off by assuming that we have complex eigenvalues. And so I have them written here as P plus QI, and then this notation here with the bar on top is a notation that we use in complex analysis, which says this is the complex conjugate. So you're going to end up getting lambda values as P plus minus QI. They're always a complex conjugate pair. And so I've just separated them here to the first and the second, where one is positive and one is negative. Now, what we're going to do is we're going to focus just on lambda. And the reality is you can work with lambda or lambda bar, and you'll get out an equivalent system. So we're going to just focus on the one with the plus QI. And what we're going to say is then the corresponding eigenvector is also going to be complex. So to find this guy, you're still going to use A minus lambda I times V equals 0, where all of these are matrices or vectors. And your vector here itself is going to be complex. So what we're going to want to do is we're going to separate it out to the real portion and then the imaginary column vector there. We're going to call those A and B. And so I made a note here that although this other vector is still, although this other eigenvalue is an eigenvalue itself, we would get the exact same eigenvector. It would just have a negative. We're not going to worry about it. And we'll talk about that a little bit more about why it doesn't matter. But first, what we're going to do is we're going to recall Euler's formula. Now, it's possible that you've seen this in other classes, but it's also possible that this is the first time you've seen this. This is a super old formula due to the ancient mathematician Euler. And it states the following, that if you take e to the I theta, where I is the imaginary number, square root of -1, what that outputs is a cosine theta plus an I sine theta. So it's actually due to Euler's formula that we've been seeing these cosines and sines pop out back in chapter 3. So if you remember when we had complex conjugate roots of our characteristic equations, A plus BI, you'll recall that we ended up having an e to the ax times C1 cosine bx plus C2 sine bx. This is exactly coming from Euler's formula. The a portion stayed up in the exponential, but then the imaginary portions came down as sine and cosine. The only thing that's important to note is we haven't been including that I term in the sine. So how does this relate to what we're talking about here with the eigenvalues and eigenvectors? Our solution is set up exactly the same as what we just noted in the last example. We want to take our eigenvector times e to the eigenvalue t. Now remember that our eigenvalue was complex, so I'm just going to replace that eigenvalue with that complex expression. Now, from here to here is just going to be using both Euler's formula as well as understanding how exponents work. So off to the side here, I'm just going to write that e to the p plus qi times t. That is e to the pt plus qit. And then by using exponent rules, this is e to the pt times e to the qit. So you'll notice that the e to the pt, it just stays right there. That's just my exponential function. But then this exponential function with a complex value in it is going to become this cosine plus I sine. So that's just using Euler's method right here. And then this a plus bi, that's just the eigenvector v. We're just replacing that with the eigenvector. The final step here is separating into the real portions and the imaginary portions. Okay, so you'll notice this I out front. We've collected all of the I terms and we've collected all of the non-I terms and written those there. And then our final step here is to take those real and imaginary portions, and each of those individually becomes our two solutions, x1 and x2. So again, up above, I said, hey, look, we could have worked with the complex conjugate lambda bar, and it'll give us equivalent solutions. But just by working with one of those eigenvalues is enough to give us the solutions x1 and x2, because we get two solutions, one being comprised of the real components, the other being comprised of the imaginary components. And so then, and I just, again, made a note here that we would have just gotten similar solutions, and then our general solution is going to be a linear combination of those two. So we take C1 times the real portion plus C2 times the imaginary portion, and we're good to go there. So what we want to do to end this video is to work out problem 12, which is going to admit imaginary eigenvalues. And I just want to note that these problems are super long. So I have the bottom of page 4, but then there's also all of page 5, and I might even run over page 5. So you might want to conserve your white space here. So we're going to start at the top. Let's go ahead and write this system in matrix form, which is x prime equals the coefficient matrix 1, -5, 1, 3 times our vector x. And then from here, let's set up our characteristic equation. We want a minus lambda I equals 0. That would become 1 minus lambda, 1, -5, and 3 minus lambda equals 0. So remember, the identity matrix has 1s along the diagonal and 0s elsewhere, which is why I'm only subtracting lambda off the diagonals. So if I set up my characteristic equation, this is 1 minus lambda times 3 minus lambda minus a negative, or plus 5, equals 0. So let's expand this out. 3 minus 4 lambda plus lambda squared plus 5 equals 0. Lambda squared minus 4 lambda plus 8 equals 0. And you can just see here by inspection that this is not going to factor. So I'm going to plug it into the quadratic formula. So negative b plus or minus radical b squared minus 4ac is going to be a 32 all over 2a. So I have 4 plus minus 4i over 2. So I get 2 plus minus 2i. So remember, we tend to write this as 2 plus 2i, and then the complex conjugate, is 2 minus 2i. So we're going to focus on utilizing this eigenvalue, but the book makes note that if you use the conjugate, you would get the same solution. It might look slightly different, but it's going to be equivalent. All right, so moving on to the next page to continue our work, we want to now take this complex eigenvalue. So I'm just going to recopy it down here. And we want to find the associated eigenvector. So remember, to find the associated eigenvector, we use the equation a minus lambda I times some v equals 0. All right, so what that's going to become is the following. I'm going to take my coefficient matrix A, and then on all the diagonal entries, I have to subtract off my lambda. On the non-diagonal entries, I don't need to do anything. And then I want to multiply this by some arbitrary vector v. So I generally write it as a and b. You could write it as v1, v2, however you want to express your vector. And then this is always, always, always going to equal 0, 0. All right, so let me go ahead and just combine the real terms and then leave the imaginary terms here. So this is going to be a negative 1 minus 2i, a 1, a negative 5, and a 1 minus 2i, multiplied by ab equals 0, 0. So at this point, we're just going to carry out the matrix multiplication. I'm going to take row 1 times column 1 and equate it to 0. So what I have here is negative 1 minus 2i times a minus 5b equals 0. And the bottom row is going to give me a plus 1 minus 2i b equals 0. So we have these two equations here. I'll just number them here in the side, 1 and 2. And when we were computing these equations to determine the eigenvectors earlier, we had seen in both cases that we got equivalent equations. So let me just scroll back up to the top. Let's look at our very first example. So if we're looking up here, these two equations, we said, oh, look, they're equivalent. They just both correspond to a equals b. And then down here, these were both equivalent. We got that b equals negative 6a. That is almost always the case, but we should check it. So coming back to where we were here. So the question is, are equations 1 and equations 2 equivalent? If they are, we can pick whichever one we want to work with and go from there. But let's go ahead and see. So in order to check this, what I'm going to do is I'm going to solve for one variable and plug it into the other equation. So the easiest variable to isolate would be in equation 2, a equals a negative 1 minus 2ib. And so now I'm going to plug this into equation 1. So this becomes a negative 1 minus 2i times this expression of a. Whoops, let's make that square brackets. And then minus 5b. And the question is, does this in fact equal 0? Right? If it does, we get 0 equals 0 and we have an equivalent system. So let's go ahead and simplify here. I have negative 1 minus 2i times a negative 1 plus 2i times b minus 5. So this becomes 1. Okay, the outer term is a negative 2i, the inner term is a positive 2i, and the last term is a minus, no, actually it's a minus 4 times an I squared. Remember, I squared is the square root of negative 1. So, or excuse me, I is the square root of negative 1. So I squared is negative 1. And so this right here is just 5, or excuse me, 4. Let's get it right here. So what I have is these cancel. 1 plus 4 is 5b. So I get 5b minus 5b equals 0. All right, so all this is showing is that equations 1 and equations 2, while they do look quite a bit different because of these complex numbers, they are equivalent. When we plug one into the other, we get 0 equals 0, which means it's an equivalent system. Hey, shh. So from here, this means pick whichever one you would like to work with, whether it's number 1 or number 2. So what I'm going to do is, since we've already started working with number 2, let's work with that one. And so what I had here was a equals a negative 1 minus 2ib. In other words, I'm going to write this as 2i minus 1b. So here's my expression for a. And then remember, our eigenvector we set up as the column vector ab. And so now what I'm going to do is I'm going to replace a with this expression, 2i minus 1b, and b is itself. All right, and here, now we just get to pick whatever b value we want, except for the forbidden value 0. Our eigenvectors are not allowed to be the 0 vector. So I'm just going to choose my favorite value, which is 1. And so that gives me my eigenvector of 2i minus 1 and 1. So we officially have our eigenvalue and our eigenvector. From here on out, what we need to do is just set up the equation for the solution. So what are we going to get here? We're going to take x of t equals v e to the lambda t. Replacing my v here, I have this complex vector 2i minus 1, 1. And then e to the lambda t. Remember what our lambda was. So we got to go all the way back up here. Our lambda was 2 plus 2i t. And now we're just going to do a whole lot of algebra. We're just going to do a bunch of simplification until we can separate our real and imaginary portions. So first I'm going to write this as 2i minus 1, 1, e to the 2t times e to the 2it. So just separating out that plus there using properties of exponentials. I'm just going to trail this eigenvector along. And now I want to utilize Euler's formula, which says if we have an e to the I theta, let me scroll back up, that e to the I theta, let me clear this out so that we can see it a little bit better. We are utilizing the fact that e to the I theta is cosine theta plus I sine theta. So let me just recopy Euler's formula down here so that we can see it. E to the I theta is cosine theta plus I sine theta. And so that becomes a cosine 2t plus an I sine 2t. All right, so here's our initial setup. At this point, we're done with Euler's formula, and all we need to do is separate the real and imaginary portions. So from here, I'm just going to distribute everything into my matrix. All right, and so I'm moving on to some blank space down here. You guys might need to flip to the back of your page. So this is now going to be a giant column matrix. We have 2i minus 1 times, and you know what, I'm going to leave my e to the 2t outside. So let's write it as cosine 2t plus I sine 2t up top. On bottom, I just have a 1, so I get my cosine 2t plus I sine 2t. And rather than chasing that exponential around, I'm going to leave it out back. And from here, I just need to completely expand and separate real and imaginary. Now, in the bottom part, my job is done. Here's the real portion. Here's the imaginary portion. Life is good. But on the top row, I need to actually FOIL this out. So let me go ahead and FOIL out the top. So my first term is a 2 cosine 2t I. My outer term, remember, I times I is -1, so I get minus 2 sine 2t. The inner is a negative cosine 2t, and then the outer is a minus sine t I. I'm just putting the i's at the back. Recopying that bottom row. All right, and from here, I can now separate out the real and the imaginary. So I'm gonna now just write my exponential out front. So the real portion up top here is a minus 2 sine 2t minus cosine 2t. This is all the real terms, that is terms that do not have the imaginary number I. And then the imaginary terms are a 2 cosine 2t minus a sine t I. And then even though it's kind of silly, I'll just kind of separate the real and imaginary here in parentheses for the second row. All right, so we can clearly see the real portions and the imaginary portions. Now we want to pick those portions off. And let me just refer back up here real quickly. So the real portion is still going to have that exponential attached, but it's whatever we got for the real portion, and then the imaginary portion. Those are going to be our two vectors. So we have the real portion of x of t is going to become our x1 of t, and that is e to the 2t times negative 2 sine 2t minus cosine 2t, and then just a cosine 2t on the bottom. And the imaginary portion of x of t, we're going to call x2. That's our second solution. We have our e to the 2t, and then we get our 2 cosine 2t minus sine t, and our sine of 2t. Oops, and I'm just noticed here, somehow I dropped a 2t. Where did that occur? Right here. So I just noticed it sneak in a little 2, not a big deal. But from here to here, somehow I lost it. And so then let me fix that right down here. This should have a 2t. All right, so we have our two individual solutions. And now we can write out our general solution either in vector form or scalar form. So for our final answer, here is our general solution. I'll write out the vector solution first. Well, first, let me just remind you guys, the general solution is always C1 x1 of t plus C2 x2 of t. And so the vector solution, which I think is actually easier to set up, just because everything is already written in vectors, is C1 e to the 2t times negative 2 sine 2t minus cosine 2t and cosine 2t, and then plus C2 e to the 2t times the imaginary portion, 2 cosine 2t minus sine 2t and sine 2t. So this entire equation would be the vector solution. And then we can also write the scalar solution, which is just going across the top and bottom. So the top row gives us x1 without the vector bar. That's going to be C1 e to the 2t times the quantity negative 2 sine 2t minus cosine 2t, and then plus C2 e to the 2t times the quantity 2 cosine 2t minus sine of 2t. And then x2 is going to be quite a bit shorter because it has half as many terms. That's going to be C1 e to the 2t cosine 2t plus C2 e to the 2t sine 2t. So two different ways to write your solution. I typically don't ask for one way or the other, so you can choose which way you want. The one thing that I do want to mention before signing off is you'll notice that there are no imaginary numbers, no i's, in your final solution. So just as there weren't any i's in our solutions for chapter 3, even when we had complex conjugate pairs, we had the cosine b plus sine b, but the I didn't show up. The same thing is true here, and that's a common mistake that I see. Students separate out the real and imaginary. So we have our imaginary portions right here, but there is no I in that imaginary portion when I separate it off. So I'll leave you with that. And this concludes our video over 5.2. And up next will be section 5.5, which is more eigenvalue method.